Hello, welcome to Module 2 lecture. The title is Science, Matter, Energy, and Systems. This is an overview of this particular module. So in Module 2 it covers a lot of information. If you haven't had a science class in a while, this is a good review of all the components that make up matter, what energy is and how it's defined and utilized, lost in our systems. And we're going to focus mostly on what an Earth system is and then environmental system in this particular module. In your book chapter readings, there's a nice profile of Dr. Jane Goodall, and in just a moment there'll be a link to a video. It's a 60 minutes interview about Jane Goodall. It's just to give you some information about what scientists do when they're actually out trying to study, explore, and explain natural systems. And she's just a great advocate for nature, and certainly has had a major impact on many different fields of science. Okay, so in Module 2, as I mentioned, there's a lot of different concepts defining science, how science is done, all these components that feed into Earth's system. So it has a lot of chemical components to it, but again, it's an overview, just kind of a refresher if it's been a long time since you've had a science class. So it's important for us to understand, as we mentioned in Module 1, that environmental biologists seek to understand nature and natural systems, including environmental systems. So to take kind of a little bit of a step backward, this involves, or not backward, but just a little more explanation. This involves a scientific process. So studying those systems, there are specific ways and methods that scientists do use and utilize in order to replicate and understand natural systems. Now, the Earth itself we refer to as a system throughout this module. There are certain inputs and outputs that we mentioned before in Module 1. One of them being, of course, solar energy. There are a couple of components here on Earth that are important to identify and address as you go through this chapter that we'll later on refer to in different modules. One of them is matter, and it's important for us to understand that matter is conserved. So as we mentioned before, things in the environment, in nature, have been, those chemicals and water itself are constantly being recycled and renewed into something else. So matter is referred to, there's a certain finite number of atoms here on Earth in the system. They may look different from time to time, but it's the same number of atoms. So this is referred to as a closed system. We can't make or take away matter, it's conserved. So there's a finite amount. And again, it may look different at different times. For example, if we were to break down the chemical components of a human being, you would find that most of our component, what we're made up of, is water. Our cells themselves are anywhere between 70 to 90% on average composed of water. Now that water we just didn't create it. It wasn't just created when you were born, or you make more as you get older, those kinds of things, or lose less as you get even older. Matter is conserved. So the water that composes our bodies, our cells, was once somewhere else on Earth. It was once perhaps in a lake or a stream, or frozen in an ice sheet, or exists as vapor in the atmosphere. So again, it's important for us to understand that it is a finite, close system. On the other hand, we have energy, and again, these are driving forces of our natural systems. In order for us to understand this, we need to understand energy. Energy, by definition, is the ability to do work, and there are two overriding laws of the study, or thermodynamics, the study of energy. One of those is the first law, and again, these are ones that I know you've heard of and certainly studied in previous science-related classes. So energy is always conserved. We can't make or destroy energy. It's constantly reused. The second law of thermodynamics is that energy is always given off. Sometimes we have what's referred to as lost energy. That's energy that's given off as heat. So maybe it's not as useful as another type or form of energy, potential energy or things like that. So when we study these things, these components that feed into our earth, our inputs and outputs that feed into our earth system, into nature, into those natural environmental systems, and we study them using a scientific process. This is typically called systems analysis, and you can build lots of models in order to explore and experiment to try to understand the natural world. And it's important for us to understand that these systems, like the earth and all of our natural systems here, are driven by feedback loops. Feedback loops can either be positive or negative. An example of a positive feedback loop, a really important one, is when that solar energy hits the earth. A lot of it's reflected off from the ice sheets. That's albedo. That's just reflected off into the atmosphere. And that prevents the earth from heating up and becoming too hot. And for all that, the water that's trapped in that ice sheet doesn't become vapor. So that's a positive feedback loop. So as those ice sheets polar caps start to diminish and get smaller and smaller, then more heat is going to penetrate and warm up those oceans. And that means more water vapor, and that means a much warmer earth than before. Now, negative feedback loops are those that are a continuous cycle. So something kicks in order to try to drive it back to a steady state. A typical example that's always given is a thermometer or a thermostat in your house. So if you set your thermostat at like 77 as the temperature, if it drops down, the temperature that the thermostat reads drops down to maybe 75, 74, it may kick in a heater, so it brings back up the normal temperature that you set it at, and then it just stops to try to keep that steady state. So when we have a balance of inputs and outputs into a system, and those feedback loops are doing what they should be doing, then we refer to that system as being in a steady state. And a lot of what environmental biologists do is try to understand what is that steady state and how do we maintain that steady state when we're talking about environmental ecosystem services. Now, there are a lot of scientists, again, that are mentioned. So Jane Goodall, you're going to watch a video about Jane Goodall's life. There are processes that all scientists use, whether you're an environmental biologist, environmental scientist, or any field that you're in. There are just a few pictures, obviously. You follow a certain process, and that process is used in order to be replicated by other scientists, other peers of yours. Finally, it's usually communicated in scientific journals. Rachel Carson, for example, was phenomenal at being able to translate scientific information to the general public for not only application, but for understanding and application of the work that they were doing. So again, just kind of some quick examples. So again, this is something that you should be familiar with or sound familiar. There may be some parts left out or some new ones put in, but it's basically called the scientific method or scientific process. So as a scientist, you or anybody that's curious about natural systems, you identify a problem, you find out what is known about the problem. So this includes like anything that's been done before, that perhaps is published, or perhaps as you go and communicate or interview others. You ask a question to be investigated. Typically these are called hypotheses, but hypotheses are based on data that's already out there, or something that you have observed that's out there already, something that's out there. There's been some preliminary data to support a hypothesis. Now, a hypothesis can be a question, it can be a model, it can be something that is testable. And then you perform an experiment to answer that question, and hopefully, often always leads to other questions, and then of course collect your data. Really important step to collect that data. You analyze that data, and basically what you're doing with analysis of data is you're looking for patterns. So you're just checking to see, are there visible patterns that you can discern. If your hypothesis, your experiment, your data has been collaborated, replicated over a long period of time, it perhaps can turn into a scientific law. A scientific law is well accepted pattern in that data, like the law of gravity or thermodynamics. You propose, again, this hypothesis to explain the data, use that hypothesis to make testable predictions, perform that experiment. And then based on your data, you either accept or reject your hypothesis. Again, sometimes you learn, often, almost always, you learn something new that you hadn't maybe thought about before. But these are generally the steps that are followed for all scientific, whether you're coming up with a new drug to treat some kind of disease, to exploring how nature works. And this is the general guidelines that all scientists follow. So it's very well regulated, so to speak, peer reviewed. It's not just people go out, test something, and come up with some kind of answer to it, and so it's science. It's just that it's well tested. It's just it's a very rigorous process that is an amazing process. Again, if it's an accepted hypothesis, then this could go on to a scientific theory. Again, it's widely tested, widely accepted. So moving on to Jane Goodall. So Jane Goodall, again, we most note her, or most familiar with her because of her work with chimpanzees. But Jane Goodall really was the woman who redefined man, or humans, what it means to be human. So before her work, it was thought to be human meant that we created and utilized tools. But because, again, of her amazing observations, her level of detail to be able to record her observations of chimpanzees, she said, there are other species out there that are highly intelligent that also use tools. So I hope you enjoy this video, and I hope you enjoy the rest of Module 2.